Luca Antiga, and I'm CTO at Lightning. Lightning, you may know Lightning because of PyTorch Lightning. Very popular. We had over 10 million downloads, I think, or like 12. It helped popularize a lot of also data parallel kind of techniques like DeepSpeed. There was an integration very early on and so on. Today, our product is Lightning AI. You can go to the website, create a free account. You get free compute, and it's a development and deployment platform. Really easy to use, and no DevOps involved. But today we're going to talk a little bit about something different, which is Lightning Thunder. It's our moonshot project that we are conducting together with a lot of help from NVIDIA, actually. Compute is evolving here. I have an MBL 72 system. It's basically made of 72, actually 144 GPUs all super connected together. So things are evolving really a lot. And today we learned that if your interconnect is different, your strategies need to be different. And so everything is very topology specific, and writing one code that fits everything is getting very, very hard. Lots of flops, large memory, bandwidth of different kinds. PyTorch is exposing APIs to exchange data using different memory pools through different paths. And you need to know all this, especially as you land on new hardware. Because next generation hardware requires you to know about those things if you want to squeeze the performance that you pay for. So that's kind of a thing you need to consider when you move to new hardware. And then fast interconnects, different data types now with listening to a great talk about quantization. And we have new data types that are supported by the hardware. So they will actually be a lot faster if you run on quantized. And so in the end, performance comes from your level of control. So how much you can control all different things. And here I mention a few things, like you start with your NN module, and you need to be sure that in doing fusions and adding mixed precisions scattered around the model, adopting kernels, and running different kinds of distributed, like 5D, you're still computing the same thing. So as a researcher, you need to apply all these things within your model somewhere, because you cannot just wrap things. All these optimizations kind of enter your model somehow. And ideally, although like researchers would like to say, okay, I have a model, it runs great on one GPU, and now just slap some optimizations on it, done. And this happened in 2019, 2020, with some of the techniques that people were using back then. Right now, it's a lot harder to just call a function and do it, because again, not only these optimizations enter your model, but the kind of optimization you want to do are task-specific, train array inference, model-specific, is it an MOE, implementation-specific, am I running on a Hugging Face transformer or Nanotron? Things change, you need to enter it. And then what hardware I'm running on, and what is the topology. So our answer to this is a project that we're building. Again, it's called Lightning Thunder. It's open source. You can just go to the repository up there and look at the state of it. Is it ready? It's not ready, but we're getting there. We're making a lot of progress. And here you can see the speed ups that we presented back at GTC this year. And it's interesting to see that, well, you get some speedups on H100s. So this is eager. This is with Thunder. This is a pre-training workload on different sizes, and we have a huge amount of models we're tracking. But the interesting thing is that as you move to B200, eager becomes faster, but the gap that you get from unoptimized to optimized, and it can be optimized with not just Thunder. You can optimize it manually with other frameworks. The point is that the gap widens as you go to next generation hardware. This kind of confirms what I was telling you before. You get new GPUs, new architecture, you need to know how to squeeze that performance up. Otherwise, you're not making the most out of your money. Okay, so what is Thunder? We call it a compiler, but compiler is kind of a broad term. Let's try to specify what Thunder wants to be. It's not too far from what DeepSpeed Compile wants to be. It's an optimization delivery system, meaning I have a model that I wrote, research style, and want to deliver optimizations into it. Okay, for what? For performance, like how to replace kernels, do fusion. Fusion is when I take many operations one after the other that will require me to go back and forth between the tensor cores and the HBM, and I just create one kernel that executes them all together, so I don't have to shuttle numbers around because bandwidth is limited. And then reducing memory and scaling up, doing different kinds of parallelism. And this is how you use it at a very high level. So we're kind of trying to get to what the desired state was before. So you Thunder compile a model, which is an NM module from PyTorch. And then you have a set of plugins that you can compose together. So that's the desired state. And so this is what usually you find yourself, this is without Thunder, what you find yourself doing. You have some model source that kind of has the what. So is it a Mamba model? Is it a vision model or whatever? And then using a combination of using hooks, monkey patching, wrapping, people kind of optimize it, so make it distributed or make it with context managers, mixed precision. And then they send it to execution. Execution can be, I don't know, PyTorch eager or different Torch compile and so on. And you have some flags here or passes that you can add to Torch compile. And so you kind of go back here, change the source, then send it for execution and see what the improvements are on the other side. What we want to do, our desired state with Thunder, and what it is today, is that from the model you get a computation trace, and then we have transforms as Python code as a first-class citizen. So we focus on these. So how do you get some internal representation of your model be transformed in a way that is developer-friendly, so that I can then get to execution with a model that is not what I started from, but it's what I started from with more stuff. And I'll show you an example, which can be Fusion Sun or using high performance libraries. For example, on Blackwell, there's all these new data types, FP8, FP6, FP4, and there's a library called Transformer Engine. That's not like it's okay, like you can use it, but you need to know how to use it properly, right? So how do I know now how to apply that library optimally to my model? That's a very deep yacht to shave every time you want to optimize things. Okay, so let's look at what happens behind the scenes. Say we have a very complicated model, a linear, relu linear, sequential. That's not very exciting, but at least it gives you a short IR. And we compile using Thunder, and I'll tell you a little bit what happens here. And then we take an example input and we run through whatever was returned by compile. It's not unlike Torch compile. And by the way, we're not competing against Torch compile. We're positioning in a different way. As a matter of fact, we are using Torch compile internally for certain things. All right, so what do we produce? Here you see a function, computation. We actually have 3 functions every time we acquire. It's a prologue that goes from NN module land to purely functional. We have a purely functional trace, and then an epilogue that goes back to object-oriented NN module stuff. And this is the function that actually computes the computation, right? There's a linear, a relu, a linear. Some information has been kind of frozen in the IR, which is like the shape and the type of the parameter. We're introducing dynamic shapes, but essentially this is an equivalent computation. And then if you want, for example, to add FSTP 0 from DeepSpeed as a transform, what do? You have to act at the, like, we want to apply it here. You need to act at different places. One is you want to move the module to your device, but you don't want to do it too early, otherwise you go out of memory. So you first want to shard your model so that one GPU only holds the right parameters for that shard, and then you want to move it to GPU concurrent. So that means that the capturing of the model and the IR needs to happen on the meta device. So not on the actual device, but on a symbolic representation of whatever are the metadata for those tensors. So we inject ourselves at this stage, at that stage, and then also at this stage, forward and backward. And we have transforms that allow you, like a transform architecture that allows you to write composable transformations also in the loading and saving stages. Because however you transform the computation also reflects on the way you save and load the parameters. Okay, so this is FSTP as a transform, how a transform in our land of transform first class citizens look like. We can iterate over the symbols in the computation that we saw, that were linear, very linear. There's a lowering to primitives that I didn't show you. And then there's some logic, like if I encounter sharded parameters, I can put some synchronization primitives here so that for the computation, I gather all the parameters from my peers, and then I do the computation, and then I deallocate things properly. So I have the full unsharded parameter to do the computation with. And so basically I go from here to something that looks like this, where you see that the sizes in the metadata have changed in the graph. So one of the nice things about Thunder is that I can take the IR, and as I apply the transforms, and there are many of them, I can follow the transformation bit by bit, so it becomes very debuggable. So, and this IR, it's actually not an actual IR. It is an IR, but it's also a Python function. So I can copy paste chunks of it and just run it, which is very useful. And then you can go one step further and say, okay, now I want to compose two transformations, one that makes something FSTP, so sharded data parallel, we heard about that today, and DDP, pure data parallel. Why would you want to do that? Because maybe your model fits 2 GPUs, but you have more than 2 GPUs. Likely you have 4 in this case, or you have 2 nodes, for example, each with 2 GPUs, if this is a fictional system, luckily. And say, I have my model can, in a sharded form, can fit 2 GPUs, but then I don't want to shard it across 4 because it would be wasteful, right? Why should I shard across 4 if I can just shard it across 2? And so I can shard it once here and once in this direction, and in this direction I can just synchronize the gradients, right? So I want to be able to express this as a composition of transforms again. And here we are reusing the device mesh that was recently introduced in PyTorch. And this is exactly what we're going to do. So we're telling our system that there's a device mesh with 2 dimensions. One is the FSTP dimension, and the other one is the DDP dimension. And now we can compose it. And here are the sharding of, it can be parameter, like the weights, the activation, optimizer state, whatever you want to shard. And so this is how it looks like. ThunderJIT is not Thunder Compile. It's kind of a lower level API that we have. I will build the plugins for this. But usually you typically operate at this level if you develop with Thunder. And then you have 2 transforms, and the order matters. So first is the FSTP transform and the DDP transform. And these are 2 independent passes that don't know about each other, but they can know how to not step onto each other's toes. And we pass the process group, so the world of 1 dimension, the FSTP1 and the DDP1. All right, so if you're curious, this is the IR, the trace that comes out of of what I just showed you. You have a lot of all gathers here, some weight primitives, and then I have a functional linear, and then a fusion that is basically the ReLU. Here we have different fusion executors. So one thing I didn't tell you is that Thunder is not just distributed, but can also do transformations to fuse things. Like for example, you can use Torch Compile to fuse conductor, or in this case we use MBFuser from NVIDIA to provide automatically just-in-time generated kernels for fusions. And then you have the other layer down here after the primitives, and here is the backward. One nice thing is that autodiff is also a transformer. So you can explicitly generate the backward graph, the backward trace or something, and you can also apply a transformation to it. And it's also very explicit like this. And you can fuse the two and so on. So the goal is to do what I just told you. So create a system that we can then apply our model with and reason about program transformations programmatically, so that we can automate going from something non-optimized to something optimized, because the way we do that is context dependent. And so we would like to get to that state. The model coverage is good, it's improving. We're working on transformers right now to make sure you can run transformers without issues. We have a few composable transforms, and we'll add more. Now we're gotten to the point where we are actually productive in writing transforms, so that's great. We support a bunch of executors like MBFuser, Torch Compile, and Transformer Engine, cuDNN, custom Trident kernels. And if you try out, your mileage may vary. It might as well be that it doesn't work for you. Please, open issues, we are very receptive, we're working on it very aggressively. So, yeah, thanks a lot.